Thanks. Forgot to record it. I forgot to record this in the morning too. But anyway, here we have solubility, yes. Electrolyte, yes. Now, sulfide, what do we do with sulfide? Well, strong bases are strong electrolytes, just like strong acids. And so strong base like sulfide, does it dissociate? Excuse me, if sulfide dissociates, what does it dissociate into? Half a sulfur here and half a sulfur there? No. In fact, bases do not dissociate. Bases hydrolyze, right? Bases attack water and hydrolyze in solution. And so sulfide's much too strong to this, so a strong base like sulfide hydrolyzes water 100%. In what forms? This is an example of an acid-base reaction. This is our base. Water is amphoteric. In this case, it's going to act as our acid. Amphoteric means it could go either way. What forms? Yeah, donate a proton. If it donates a proton, what are we left with? Hydroxide, yeah. And hydrogen sulfide ion. HS minus. Excuse me. And so this is the leveling effect. All strong bases are going to hydrolyze water to form hydroxide, the strongest base. And so if I have amide, amide's going to do the exact same thing. Amide will attack water to form hydroxide. All these form hydroxide, a common product. Therefore, they're all the same strength in water. Just like, you know, HCl. HCl hydrolyzes water. HCl is too strong to exist in water, so it hydrolyzes water to form hydronium and chloride, right? In fact, all of the strong acids do the exact same thing, and all of them form hydronium. The same amount for a given concentration. And so that's a leveling effect there. All right, now, the reason why I didn't write potassium sulfide, AQ, is because this doesn't exist. What exists is potassium hydroxide and potassium hydrogen sulfide, not potassium. If I took solid K2S and put it in water, actually I wouldn't touch it with my hand, but if I did that, this is what I'm going to get. Now, this is still a pretty decent base, and we have acetic acid present. And so if I have hydroxide and acetic acid, there's going to be more reaction. And so let's talk about the next reaction here. What's a stronger base, hydroxide or hydrogen sulfide ion? Well, that we might have to look up. But you should look at this chart very carefully because, you know, there's some confusing things about this chart. If I look at hydroxide here, hydroxide's grouped with the acids. You see, this is the acid column. But hydroxide is also grouped here with the bases. This is the base column. And so why is hydroxide both in the acid and the base column? Because hydroxide can go either way. Hydroxide can be an acid or it could be a base. If hydroxide acts as an acid, then you need a much more powerful base than hydroxide to react with it. And so you need something like hydride or methide to react with it. Extremely powerful bases. But anyway, it's rare. Normally we think about hydroxide as being a base, and a powerful one at that, and that's correct. And so when we look at the base, we see HS minus here, hydroxide here. Hydroxide's a more powerful base. And so if we're going to attack acetic acid, both of those species can attack acetic acid because they're both bases. Hydrogen sulfide is also amphoteric. We'll get a lot more practice with this chart. And so acetic acid is going to be first attacked by hydroxide. What forms? It looks like we're going to form acetate and water. in a net ionic equation like this, what we have to do is we have to make sure the charges and the atoms balance. So the net charge on the left is -1, net charge on the right is -1. Okay. Acetic acid can also be attacked by hydrogen sulfide ion, because hydrogen sulfide, this is tricky, because what their identity is depends on what they react with. And so this is an example of acid-base reaction. The driving force for an acid-base reaction is we go from stronger acid, stronger base, to weaker acid, weaker base. And so here's our base, sulfide, here's our acid, water. What's the base and acid over here? Is hydroxide the base and HS minus the acid? And so what we do is we do conjugate pairs. If water's the acid, then its conjugate base is hydroxide. So this is the base. And if sulfide is the base, then its conjugate acid would be HS minus. This would be the acid. When we compare sulfide versus hydroxide, this is a stronger base, this is a weaker base. We compare water with HS minus, water turns out to be a stronger acid, HS minus with the weaker acid. That's in the context of this reaction, but both of these species are amphoteric. And so HS minus now reverses its role. Here it was an acid, but now it's going to be a base, because now it has acetic acid to attack. And so HS minus can attack the acetic acid. When that happens, it's going to form acetate and H2S, gas. And so what we'll do is we'll add up all these reactions and see what we get as a net reaction. And so if we add up these reactions, we'll take this reaction with the K2S. The K2S plus the water is going to form, actually I'll just do it as a complete equation. The K2S and the water, I'm going to combine those earlier equations, is going to form KOH and KHS. Actually, I can't. These are net ionic, this is complete. Let me redo this, sorry. We're doing this, I'm going to go K2S goes to 2 potassiums plus the sulfide. The sulfide plus water goes to HS minus and OH minus. Now let's add them up. I add these up, and what do I get? I get a mess. Been confusing. But those cancel. Those cancels. HS minus cancels. OH minus cancels. And so the net reaction here is going to be K2S solid plus 2 acetic acids yields 2 potassiums plus 2 acetates plus H2S. The waters cancel. And so when I look at this final reaction, the final reaction is the same as the initial reaction we wrote. Do you see that? And so a lot of stuff, extra stuff going on here, but in the end, that was it. So we could have ignored all this other stuff that was going on, this what we call the hydrolysis, the base hydrolysis, right? And just wrote the net reaction. Well, that's the same thing that's going to happen with this. Ammonia, you should recognize, ammonia is a weak base. What do weak bases do? Weak bases hydrolyze water. And so when I think about ammonia, one of the first things I think about is ammonia and water. This is going to produce some ammonium and hydroxide. Well, a strong base, it goes 100%. Weak base, this side's favored. But this is what happens. And it turns out that hydroxide likes magnesium ions. When hydroxide sees magnesium ions, it likes to form a precipitate of magnesium hydroxide. And so I predict I'm going to form magnesium hydroxide in this reaction. But what I'm going to do is, I'm not going to worry about this hydrolysis here. What I'm going to do is this. When I write this reaction out, it's going to just be magnesium nitrate plus ammonia plus water. Q. And then I think of this ammonia and water as producing some ammonium and hydroxide. And so I imagine this as being some ammonium hydroxide, enough hydroxide to precipitate. And so this is magnesium nitrate plus ammonium hydroxide. It's going to yield magnesium hydroxide plus ammonium nitrate. And to balance this out, I need 2 hydroxides. So I'm going to need 2 ammonias, 2 waters to form 2 ammonium hydroxides. And this will give me 2 ammonium nitrates here. And so this is what I don't want you to do. I don't want you to write this. Yes, I understand that there's going to be some ammonium hydroxide formed there, right? But I don't want you to write ammonium hydroxide here as a reactant. The reason I don't want you to write ammonium hydroxide is this. If you wanted to carry out this reaction, would you go to the chemical store and buy ammonium hydroxide? Or would you go to the chemical store and buy aqueous ammonia? You'd go to the chemical store and buy aqueous ammonia because ammonium hydroxide is unstable. They aren't going to sell that to you. And so we buy ammonium. The same thing. Are you going to buy potassium sulfide or are you going to buy potassium hydroxide and potassium hydrogen sulfide? Mix. 50-50. No, you buy potassium sulfide, you mix it with water, that's what happens, right? And so some of these details we kind of leave out, like these hydrolysis reactions that occur, but we know that they happen and they're very important in the chemistry of it all, but we just look at it net. And so we aren't going to worry about this, but we know it reacts like that. We write the reactants that we're actually going to purchase in here. And so when we do that, now, a lot of these are aqueous. And so what you could do is you have a choice. You could leave all the aqueous off, this is a solid, and write the non-aqueous states, liquid, solid. Or you could write all the aqueous in. But you can't write half the aqueous in. Like say, for example, you write aqueous here and you don't write anything for ammonia, then you're going to get deducted points. And so either write all of them in and don't miss any, or leave them all out. I leave them all out. All right, so this would be the complete equation. And then we would have the ionic equation, which is just Mg2 plus 2 nitrates. We ionize a strong electrolyte, nitrate salts are soluble. Ammonia, weak electrolyte, so we leave it alone. Water, non-electrolyte, leave it alone. Magnesium hydroxide is an insoluble salt, so we leave that. Ammonium nitrate is a soluble salt, so we'll split that up. 2 ammoniums and 2 nitrates. Then we cancel out the spectators. Nitrates, they're spectators. This is the complete equation. This would be the ionic equation. In that ionic equation, we remove the spectators, so we're just left with magnesium ions plus ammonia and water. 2 of these yields magnesium hydroxide, solid, plus 2 ammoniums. Then we make sure it's balanced. The charges should be balanced, plus 2 on the left, plus 2 on the right, and the atoms should be balanced. So this would be it. Is there a driving force for this? Yeah. The driving force would be precipitation of magnesium hydroxide. So yeah, I know it's important, the hydrolysis, of ammonia, but we don't write that in there. In fact, if we did write it in there and then add everything up, it's going to get this, the same net equation, net reaction. Right. Let's look at this one. This is lead iodide with hydrochloric acid. Okay, is that lead 2 iodide or lead 4 iodide? I made a mistake, but what's more common, lead 2 or lead 4? Lead 2 is much more common. And so this is lead 2 iodide and HCl. What's lead 2 iodide? Solid, liquid, aqueous? Gas? Solid. Iodides are insoluble. Lead iodides are insoluble. So PbI2 solid plus HCl would be aqueous. What's this going to produce? It's going to form lead 2 chloride and HI. Okay, lead 2 chloride. Precipitate? Yes. And so, what can I say here? I got a driving force. Can I say that precipitation is my driving force for this? Why not? In the last one where I had magnesium hydroxide, it was simple. It was precipitated magnesium hydroxide. In this one, why can't I just say the same thing? I can't. I can't call this a driving force because I'm destroying one solid and forming another. And so what do I have to do? I could look at the acids. Yeah, let's look at the acids. Which is stronger acid, HI or HCl? Do you guys remember? HI is a stronger acid than HCl. And so this is a stronger acid, this is a weaker acid. And so I could say that, oh, there's no driving force because I'm going from weaker to stronger. I should be going from stronger to weaker. But this would be wrong too. Why would that be wrong? Because of the leveling effect. It doesn't matter because HI and HCl yield exactly the same thing in water. If I have HI is too strong to exist in water, it's too strong to exist in water, it's all going to be converted into hydronium and iodide. HCl is too strong to exist in water. It gets converted into hydronium and chloride. We're both the same. It's a leveling effect. So if I have 1 molar HI, I'm going to form 1 molar hydronium. 1 molar HCl forms 1 molar hydronium. 1 molar hydronium versus 1 molar hydronium, which one's stronger? They're the same, right? Can't tell the difference. So the leveling effect, we wouldn't say that. They're both the same strength in water. And so now we're stuck. We have to look at the precipitate. Okay, now precipitates, you guys remember lattice energies and that type of stuff? Lattice energies, we have lead ions, which are 2 plus, and iodides, that are 1 minus. And we got an ionic bond, right? Link it together. And then we can compare this. This is a 2 plus here, and then chloride is a 1 minus. So it's the same, except chloride is bigger or smaller than iodide? Chloride's smaller. If chloride's smaller, then which bond is stronger? The iodide or the chloride? The chloride bond is going to be stronger. Why? Yeah. Well, you could look at Coulomb's law. Coulomb's law says, the charge, the attraction depends on the charge and the distance. It's the distance between center of charges. Or in other words, I like to think of it in terms of charge density. If you have a -1 spread out over this volume versus -1 spread out over this volume, we're going to have a lot more negative charge density in the smaller volume than in the big volume. And having more negative charge density means there's going to be a stronger electrical attraction. Therefore, it's going to be a stronger bond, right? In general, that's what we expect. The higher the charge, or the higher the charge density, the stronger the bond. Look at your solubility rules. Carbonates, phosphates, chromates are insoluble. Those are -3, -3, -2, right? So when you look at your solubility rules, the pattern is the higher the charge, the less soluble. But then there's some weird stuff. The lower the charge, group 1, +1, all soluble. But the weird one comes from silver chloride. You know, silver chloride, why is that insoluble? Silver's plus, chloride's minus. Shouldn't this be like sodium chloride? Sodium chloride plus minus. Is it because of the size? Silver ions are very small. You know, the size decreases as we go right to left. So silver ions are very small, so maybe that's it, or what? Well, this is looking at bonding, assuming it's 100% ionic. 100% ionic is just the electrical charges attracting each other as these balls. But bonding isn't always 100%.